Alright, so we're going to talk about the problem of area and then ultimately definite integrals now. So first of all, the central question that we begin with is what is the area bounded by some function y equals f of x for a less than or equal to x less than or equal to b? Geometrically I'm assuming f is non-negative here for a bit, but of course you may recall the formulas that we arrive at soon actually make sense whether f is positive or negative or 0. Alright, so here's just our starting point, roughly speaking. You got some graph. I don't know, maybe it looks like this. Alright, here's A, here's B, alright. And the idea, of course, is, well, if I had like a graph paper or something, you could kind of envision chopping, and so we're trying to find the area, right, let's see here. That's stuck between these vertical lines, x equals to a, y x equals to b, the x-axis down here, right, and the graph y equals f of x. So what's this area of this kind of curvy region? So if this is graph paper, right, you could just kind of count up the number of boxes and get an approximation, right? And so roughly speaking, that's what we do. You just chop this interval up into a sub-interval, right? So let's see here. We let x naught equal to a. We let b equal to x sub n, right? And then you put, say, this is x1. This is x2. There's some break, let's say, in the graph here. And then out here we've got xn minus 1, xn minus 2. To keep things simple, I suppose that the distance between these partition points is the same everywhere, and that distance is what we call delta x. So delta x would going to be, well, how many do you got? You have n total subintervals, right? So if I take b minus a over n, that's the width of each interval there, right? And the formula for the jth partition is simply this: x sub j is equal to x sub naught, which is a, plus j times delta x. All right. Let's see here. As a check on my formulas, what happens if we put in n? X sub n is equal to a plus j is equal to n delta x. Well, b minus a over n. Check it out. So the a's cancel and we get b. Good. That's what I'm saying. So then the name of the game is, now that we've got this partition of the interval into n subintervals, what you do is then you have to you got some choices to make, right? And so there are three main popular choices. We'll talk more about this in Calc 2, but just, there's kind of three natural choices, I guess. You use left endpoints or right endpoints or midpoints. Maybe you didn't see that in Calc 1, it's no big deal. But more generally speaking, what you want to do, just to be kind of magnanimous, maybe you, or I don't know what the word is, fair, you pick some point in each subinterval, let's say x1 star, and that gives me this right here, and so there, that green box is kind of an okay approximation for the area under the red curve right there, right? Then I don't know, maybe it's like here somewhere. So the height of the second box, right, would be f of x2 star. Now, what is x2 star? I'm not saying exactly. I haven't given you a formula for the function or anything, but something like that. And so basically, these sample points, what you want is xj star, right? The sample point, which you're defining the height of the box by, to be some element of the interval, which goes from what? From xj minus 1 to xj. It's some kind of sample point. It could be any point in there, really, generically speaking. Okay, so we're doing that, and of course, if then we wanted to calculate the area under the red curve, an approximation to the area would be what? So this is what's known as a Riemann sum. The nth Riemann sum here would be something like the sum, right, of the areas of the boxes. So that's the sum j equals 1 to n, all right, and the height of the box is f of x sub j star, right, and what's the width of the box? Well, it's just delta x every time, right? And so there you go, this is the nth Riemann sum, which is not a unique thing as I'm setting it up, because, like I said, you know, the selection of the sample point can be taken randomly. All right. Now that begs some analytical questions, which I'm going to sweep under the rug here. If you want a more careful treatment of integration, you should study something called measure theory. There is a little bit of that in your textbook, a little bit more than I have to say here. Talk about upper and lower sums for the integral, and if they both converge to the same thing, whatever converge means, you know, you get a well-defined integral. Anyway, I don't want to say too much about that. I'm just going to give you sort of the usual slightly sloppy definition of the definite integral. So the idea then, of course, is that as n goes to infinity, a couple of interesting things happen. As n goes to infinity, of course, you can think about it, if we chop the area under the curve more and more precisely, more and more finely, then we get closer and closer to the area, right? That's the idea. And on the other hand, the delta x goes to 0, right? So the number of things we're adding up goes to infinity, but the value of each one goes to 0, all right? But this is done in such a way that these two things balance out to give you something finite. I mean, it's geometrically clear that the area under the red curve and bounded between these dotted lines is something, right? I mean, surely if I drew a rectangle with this height and that width, right? Like, let me clutter my picture with this for just a second here. If I draw you this rectangle, right? This guy. No, I messed up my picture. Oh well. If I draw that rectangle versus I draw this bigger rectangle, right? Like that. The whole thing, right? So the blue rectangle is a subset of the orange rectangle. And suppose this is M and this is big M, right? It's pretty clear that the area bounded by the curve, which is now kind of lost, oh well, you can rewind the video if you want, it's got to be something like this, right? M less than the area that we're interested in, less than big M. That's not quite right, because it's M times what? That's the height, the width is B minus A. Sorry, kind of ugly, but you know, certainly we have that estimate. Geometrically, that's clear. The area has to be somewhere between those two things. And those two things exist for a continuous function, because a continuous function, again, obeys the extreme value theorem, so it attains a minimum and a maximum, right? So m, little m and big M exist. The function's bounded on the closed interval. All right, anyway, obvious geometric comments aside. The area, right, is going to be equal to the limit as n goes to infinity, right, of some, and you know, I wonder, did anyone ever define that kind of limit carefully for you? Maybe not, but it's somewhat clear geometrically what's meant by that. I actually will define limits like that, a limit as n goes to infinity, a little bit more carefully later in Calculus 2, so I'll just leave it at that for now. But this, folks, is the Riemann sum. As n goes to infinity, we don't get an approximation of the area, we get the actual area. And then, this is, by definition, the integral from a to b, all right, of f of x dx. All right, so there you go. That's the definition of the integral in terms of a Riemann sum, as is motivated by the study of area bounded under a curve. Now, on the flip side of things, I mean, I try to motivate this, of course, using a positive function, but it's fairly clear that this formula still makes sense, whether f is positive or negative. What does it do? It just counts area that appears under the x-axis, quote-unquote, area, quote-unquote, as negative area. You know, some people would like to say, and I guess I'm one of them, that this actually calculates what you might call as the signed area. Signed area under y equals f of x for a less than or equal to x, less than or equal to b. So just as an example of that, non-trivially, so example, if you were to look at, say this, y equals x, right? here's 1, here's minus 1. Just some kind of obvious from the geometry of it here, right? So this has signed area 1/2, because base times height is 1. 1/2 base times height gives me area of a triangle. This has signed area minus 1/2, so that gives me integral from minus 1 to 0 of x dx is equal to minus 1/2. The integral from 0 to 1 of x dx is equal to 1/2. Of course, the integral from minus 1 to 1 of x dx is equal to 0. Just as kind of a warm-up example there. All right, so that's the definition of the definite integral in a nutshell, and that's wow, it's kind of intimidating. We have to calculate this infinite sum, right? But of course, that's not the end of the story, and I'll pick up on that in the next video. Thanks, guys.